Hello, I'm Alan Stahl, a Senior Principal Scientist in Research and Development at Biosciences. In this series, we've reviewed the principles of panel design and general workflow. Now, let's explore some best practices for data analysis to support you in your experimental journey. So now you've set up your instrument correctly, designed a great panel, and run your experiment. However, when you look at your data, you have a hard time identifying some of your populations. How can this happen? How you display your data can have a major impact on your ability to interpret it. Let's look at some data display options and how they can help you in your data analysis. Flow cytometry data is typically displayed as one-dimensional histogram plots or as two-dimensional or bivariate plots, which show the correlated expression of two markers and can distinguish multiple subpopulations within a sample. Histograms are used to display single marker expression as measured on the x-axis, typically of a gated subpopulation. When comparing histograms with or without overlays, there are multiple options for the y-axis. Using the Auto option, the software automatically selects the y-axis scale for each graph. This is easy, but can lead to misleading comparisons. Using Max or Manual lets you specify the overall maximum value for all graphs, while Modal sets the biggest peak in each histogram to be equal to 100%. The benefit of the modal is that the profile of each histogram is independent of the number of events analyzed, and this makes it easy to overlay the histograms. Bivariate plots show the correlated expression of two markers, as seen here with CD197 and CD45RA on CD8 positive T cells. The early display standard for bivariate plots was dot plots, where each dot represents a single event on the XY axis. However, this can now be accomplished with the use of outlier options and contour plots, as can be seen later. A more informative way to display bivariate plots is to use contour visualization. The advantage of contour plots is that they allow you to easily assess the relative size of different populations and give insight into the exact boundaries between the populations, enabling more accurate gating. In the dot plots shown, it is not possible to easily distinguish the distinct populations of CD8 positive effector memory and central memory cells expressing varying levels of CD45RA. But when the same sample is presented as a contour plot, one can now easily discern distinct populations of different sizes. Using this plot, we can then cleanly color code the different populations and then look at the expression level of third or fourth marker, here using PD1 in a histogram. There are three different flavors of contour plots. Most commonly used are the standard contour, plain lines with outliers, or pseudocolor. As shown earlier, the standard contour plots are the easiest to interpret and to define gates between populations. Pseudocolor can also show populations, but has similar limitations to dot plots when trying to decide where to draw gates. Using contour plots with lower percent contours, such as the 2% shown on the right, can help define small populations, as seen in the red box. Another disadvantage of dot plots, whether single color or pseudocolor, is that the visualization of populations is very dependent upon the number of cells collected. Compare these plots with 2,000 or 20,000 events. At 2,000 events, you begin to lose the resolution of distinct subpopulations. However, when displayed as contour plots, the subpopulations are equally seen with 2,000 or 20,000 events. Once you've decided what type of display to use, you need to select which numeric axis you're going to use. Data can be scaled as linear, logarithmic, or a combination of both known as biexponential. Linear scaling is rarely used for biological data. Logarithmic scales are still the most commonly used, allowing data display over a wide dynamic range to be easily displayed. The major limitation of log display is that it compresses data at lower values and cannot display data values of 0 or below. As seen in this plot, where there are a significant number of events below 0 due to compensation, logarithmic display can make the data look aberrant. This can result in single populations actually appearing as two distinct populations, as seen in this plot shown in the red and green boxes. This problem can be mitigated by scaling methods such as biexponential, which combines the best characteristics of both linear and log into a single scale. As seen here, higher values are in a log scale, but as they approach 0, the scale shifts to linear around 0. Values significantly below 0 shift back from linear to log. There are a number of mathematical variations of this combined scale, such as biexponential or logical. Using the data shown earlier, we can see that when plotted in biexponential, what appears to be two populations are in fact one. Using biexponential, it is very easy to visualize whether compensation is correct and how much spillover spread there is. These biexponential mathematical models allow the user to adjust the area around and below 0 via a scaling factor. In Flojo software, this is called the width basis. Changing the width basis will visually change the apparent spread as seen in this figure. Here we see the exact same data displayed with different biexponential width bases. The graph on the left appears to have very little spread in the x direction, while the one on the right has a lot. These are the exact same data. Notice the values around 0. The data on the left are more compressed around 0 compared to right. When comparing exponential plots, always look at the axes to make sure that they are equivalent or similar. In this example, the spread of two positive populations of the samples looks very similar, but in fact, the two populations spread are very different. Notice how different the y-axes are, because with different width bases which were used, the data on the left are compressed compared to the data on the right. In most cases where you want to compare data, it is best to manually adjust the biexponential scales to be identical and then apply that scale to all samples as shown here. In the top panel, the spread of positive populations looks very similar. However, adjusting the biexponential scales to be equivalent, we can easily see that the spread in the left panel is much greater than that on the right. Following these tips should help you get the best data from your important experiments. For more information, please visit the BD Biosciences website, bdbiosciences.com.